this is Jared Big Nasty Murphy here with his wise piece of chalk and his fancy clicker. And this is a howdy-do darn tootin' Fayette County concept of radioactive decay. Now, I'm sure you've heard of radioactive decay at one point, probably in some kind of fancy Indiana Jones movie or something of the sort where they do a bunch of scientific stuff and you have no clue what's going on. But I'm going to explain it to you today. And Redneck Randall's also there. So what the heck is radioactive decay? Well, I'm going to tell you so you don't have to worry about it anymore. Radioactive decay is, in layman's terms, the breaking down of a molecule by emission of radiation over a long, long period of time. And the substances that are normally used in this are fossils, rocks, or grandma's fruitcake she sent back in the day, which is probably 80 years ago, and your mom just threw them in the closet and forgot about them because she doesn't like fruitcake. Don't tell grandma. Okay, so anyway, RD, which is radioactive decay, I don't want to say radioactive decay 50 times to bore you to death, has two asymptotes, one on the x-axis and one on the y-axis. So essentially, it's never going to be negative on either the x or y. And Homer Simpson is obviously a supporter of math, as you can see here. Some might not know that. I mean, he's obviously very intelligent there. And throw credit to Mark Groening, because can't just mention something and not give credit. Now, to the bare bones. Radioactive decay. You like Skelly Man? I think he's really pretty. Okay, so here's what it is. Radioactive decay is represented by the equation of L equals N times 1/2 to the T over H power, where L is the amount of substance left after T years, N is the starting amount of substance, T is time, H is half-life. We'll write this down here so we have it for later. Alright. So, solving a radioactive decay equation. Well, it's relatively easy if you are given the N, the T, and the H, which is what most problems will have. But if you're an actual scientist, it's going to be a lot harder, but I'll get to that in just a second. For this one, all you have to do is plug the numbers into the respective spots, like going to plug the original starting number of things that you have, or the weight of the mass that you're trying to figure out, and the time that it took to get there, and what the half-life of said substance is, which I'm not really sure how they figure that out, because nobody's been alive 30,000 years to figure out carbon. But that's not mine to judge. Alright, so here's where the crap hits the fan, so hold on tight. Alright, so we're given this one, and we are not given this one. So we're not given the time. So how on earth are we going to do this? We're going to do it like scientists. They aren't given how long it is. They have to figure out how old, or when these dinosaurs roamed the earth, and when we got scared and hid in our caves. So, let's see here. I have to pull up your example. Alright, so L is 5 right here. It's what we end up after T years. So right there I tell you we aren't given T. We'll go ahead and make that an exponent. Then the half-life is 1,000. Sorry, I'm going out of order a little bit. And the stuff that you have at the start is 20. Oh yeah, and I have to throw this little half there. There we go. Okay, so what are we going to do to start this thing out? We are going to divide on both sides by 20. Since that's the algebraic thing to do, making it a quarter equals 1/2. to the t over 1,000 power. Alright, so great, I'm stuck. What the heck do we do here? Well, there's two ways to do this. If you're an expert and already know everything about radioactive decay, then you can figure this out that it's going to be 2,000, since 1/2 times 1/2 equals 1/4, making it 2,000 over 1,000, which simplifies it to 2, which, if you understood that, then that's fine, but there's an easier way to do it. So, we're going to pull out a fancy trick that you probably, you might have heard of it. It's called a logarithm. And the logarithmic formula is log a of y, the log of a, the a log of y equals x. There we go. And that is representative of y equals a of x, which, hey, that's what we have here, right? Y, just a regular y, and a, 1/2, x, t over 1,000. Well, I'm going to plug this in for you. So log, let's see, where's our a? 1/2, y, 1/4, equals t over 1,000. Well, that looks a lot better, doesn't it? So, if you don't know how to solve a logarithm, then I'm going to teach you right now and make this a little bit easier. So, we're going to have to figure out what kind of exponent we would have to attach to 1/2 to create 1/4. So let's try a couple here. 1/2 times 1/4, 1/2 times 1/2, 1/2 times 1/2 times 1/2. Alright. So I'm going to evaluate these real quick. Okay, so which one's it? Well, obviously this one, because it's 1/4. So what we need is a power of 2, since we have 2 1/2s. So I have to rewrite it again because I rudely intruded on it. Which really, we don't need that anymore. So t over 1,000 equals 2. And we can use the fancy property of whatever it's called, that we take this 2,000 is equal to 1x. And there's your answer. And by the way, I actually know what this is. I didn't just pull it out of nowhere. It's a real property. I just don't know the name of it. Very useful for this. And it's pretty sweet, huh? Those are some pretty good pecs, right? I've been lifting a little bit, and I'm trying to get there, but just haven't yet. Anyway, I hope you learned from and enjoyed this experience, and I hope to see you for my next one. Have a good one.